Before you listen to the podcast, I want to ask for your input. Teagasc have launched a survey to help identify the impacts of the very wet autumn. The loss of winter crop area will be compounded by a lack of seed for spring cereals, which may lead to unsown land on many farms in 2024. Teagasc are asking all tillage farmers to participate in the survey to tell us how much land which was destined for spring crops is still unsown and your intentions for this area in 2024. The link to the survey is in the show notes. Hello and welcome to the Tillage Edge with me, Michael Hennessy. For this episode, we're going to repost an episode we did with Mike McLaughlin, a soil scientist from Australia. Mike did a particularly good session around soil chemistry and its interactions, and I think it's worthwhile listening to again.
The things you see actually when you look at a soil is clay, silt, sand, and organic matter. And the clays are obviously very important because they've got a lot of the nutrient holding capacity in soils and a lot of the water holding capacity. And similarly, organic matter's got a lot of the nutrient holding capacity and water holding capacity. But it's really the interaction of clay with the silt and sand and the organic matter that makes up soil fertility in a physical sense as well as a chemical sense. So if you take any one of them away, you end up with a problem in terms of agricultural production. So it really is a team activity in soils. As I said before, clays are critical because they're the largest surface. They're very small particles, so they have a very big surface area, and they've got a lot of surface charge, and that helps to retain nutrients in soil from leaching. And organic matter, originally organic matter comes from the natural vegetation that's on the land, but then we add organic matter to soils as well. And don't forget, when you grow a crop, about 40 to 50% of the carbon goes below ground. So if you're taking up, you've got 11 ton or a 12 ton wheat crop, and you've got the straw on top of that, maybe 20 tons or 25 tons of biomass, you've got 12 to 15 tons of carbon biomass going below ground as well. So there's a huge input of carbon through agricultural production that we forget about. Agricultural production doesn't take carbon away from soils necessarily. The production part of it puts it into soils. It's the tillage part of it we've got to be careful with because that tends to mineralize the organic matter.
Okay. And from the point of view then, I suppose when you delve in a little bit deeper to soils, most farmers would be very familiar with pH. How does the pH influence or vary on those different elements, and how important is that in terms of helping the availability of the nutrients within that soil?
pH is often, soil acidity or alkalinity is often called the master variable in soils because it controls the availability of so many nutrients for crop growth and also can control the activity of microorganisms in the soil. So when soil pH is low, you've got problems in that low pH actually dissolves up clay in soils. So a lot of clays are aluminosilicate minerals or aluminium hydroxides even. So it's the composition of the actual clay itself is aluminium with silicon. And if you get a very acid soil, you actually break the clay mineralogy apart and the aluminium gets released into the soil pore water, which can make it toxic to plant roots, but it also allows the aluminium to move out of the soil. So effectively you're leaching your clays by low soil pH. That low pH also changes the charge on the soil particles, so the clay and the organic matter, and that can affect how the soil holds nutrients. So acid soils in particular are going to bind phosphorus very strongly because of that very reactive aluminium. And also they're going to bind some of the microelements, for example, things like molybdenum, which is important for nitrogen fixation, is bound very strongly in acid soil. So it affects that availability of nutrients. You don't want a soil to be too acid, and you don't want it to be too alkaline. On the alkaline side, you get in trouble with trace elements, the trace elements that have got a positive charge on them. So that's things like zinc and copper and manganese. And they're going to be a problem in very alkaline soils because they get bound very strongly, and so does phosphorus. So at the two ends of the pH spectrum, you've got issues with nutrient availability. And also microorganisms aren't very happy when it's very acid or ultra alkaline as well. So we really want to keep soils in that mid pH band between pH 5.5 to 7.5 is sort of the sweet spot for pH.
Okay, and even up as far as 7.5. I suppose most people here would probably get a little bit worried once it gets up as far as 7 in terms of the availability of P. But would you be happy enough in up as far as 7.5 in those circumstances?
Well, you see, in Australia, we've got soils of pH up to 9.5. When I'm talking pH extremes, that's
okay.
You've got major problems when we've got huge areas of soils of pH 8.5, which is a major problem for phosphorus availability. But yeah, once you get above 7.5, then that's where the phosphorus availability starts to dip off. So, and usually that's soils that are naturally developed on limestones, or if you've over-limed a soil, if you've added a lot of lime to a soil, you're going to have lots of reactive calcium carbonate. And that can be a problem then for phosphorus availability and trace elements.
And then when it comes to, say, a farmer has a highish pH soil, as in 7 or maybe up as far as 7.5, we don't have probably too many soils here that are too much above 7.5. Would it make any difference the type of phosphate that's used, whether it's diammonium phosphate or triple superphosphate? Does the source really make any difference in terms of trying to help the availability of that phosphate through the season in those higher pH soils?
Yeah, in a higher pH soil, triple superphosphate is basically calcium phosphate, whereas DAP, diammonium phosphate, is ammonium phosphate. So very different reactions in the soil when the granules first go into soil. The DAP, initially it's slightly alkaline. And it's interesting, actually, DAP slightly alkaline reaction around the granule, but then because of the ammonium in there, as that gets converted to nitrate, that will acidify the soil, which on a high pH soil is good because it brings it more into that sweet spot. Interestingly, TSP is acid to start with because of residual phosphoric acid in the granule, but then it's becomes quite alkaline over time because of the reaction with the soil, and there's a lot of calcium phosphate in the product itself. So because you get calcium in the soil and calcium in the product, that can reduce the diffusion of P a little bit. So it's a small effect in terms of the chemistry, but it has been shown that applying ammonium with phosphorus is very beneficial to crops. There's a synergy of the nitrogen with the P being placed together. So the ammoniated phosphates tend to do better than TSP. Obviously, if you've got a legume crop that doesn't require much nitrogen, TSP is probably more preferred because you don't need to pay for nitrogen.
Okay. And in terms of the, when it goes on, it turns slightly acidic over time. And when that acidity reduces, then how long does it take for that phosphate to bind in those high pH soils? As in, I suppose thinking, could a grower expect to see some of that phosphate still being available 3 or 4 months later?
Yeah, look, the reaction when a granule goes in soil is really very, very quick initially. So the granule dissolves almost immediately within 24 to 30 hours. Most of the phosphorus would have come out of the granule itself and moved into that zone of soil around the granule. So initially you get reactions called precipitation reactions occurring. And in an alkaline soil, it's calcium from the soil precipitating with the P. And effectively you're turning it back into, first of all, it's triple superphosphate, but then it becomes other less soluble calcium minerals. So that precipitation can happen quite quickly. But then over the longer term, the soil will tend to dissolve up some of the precipitates, and it gets held by other mechanisms in the soil, a surface reaction. And that surface reaction basically is stronger with time. So it's one of the unfortunate things with phosphorus is the binding does increase with time in a low fertility soil. So we do have to build up the soil phosphorus bank, if you like, because of that binding. In a lot of cases, it's not irreversible, I should say. Some people tell you there's irreversible binding. It's not, because you do get some of the phosphorus back from previous applications. It might be a small percentage, but if you apply phosphorus over decades, or in some places centuries, all those previous phosphorus applications do contribute to the crop uptake eventually. So the actual efficiency of P use isn't as low as we think. So if we measure efficiency of P use in a single year, and we can do that using tracers, we might find only 10 or 20% of the P gets into the crop. But if you look over, say, a 50-year period, the P balance efficiency of a system might be 80 to 90%, where you're putting on 20 kilograms of P and you're taking off 18 kilograms of P in the grain, and you're in a sort of an equilibrium situation. Quite often, that's in Australia, that's called the maintenance phase, where you've got the soil into a balance with the input equal to the offtake. So on that long term, the P efficiency is quite high. In the short term, from that single granule, it's quite low. So yeah, you need to be aware that phosphorus efficiency isn't quite as low as we're made to believe sometimes.
Okay, so I suppose that really comes down to, and as you say, the background phosphate, the background level needs to be there in the first place. And I suppose the tricky thing there is what's the sweet spot in terms of that background level, so you could just do that bare topping up type scenario and you get this 80% efficiency.
Well, yeah, that's why we do soil testing. I mean, that's why it's critical to do soil testing for phosphorus availability, because if you've got a high soil test value, and you've got the 4 tiers in Ireland, if you're in the top tier, you probably need less or no P. And if you're in the very first tier, very low phosphorus availability in the soil, you obviously need to add a reasonable chunk of P to get the crop up to its full potential. So the point of soil testing is to get a measure of that availability of P from past applications. For example, at the moment, phosphorus prices are quite high. So a lot of farmers are not adding phosphorus to soil because of the cost. If that went on for decades, you would slowly see soil P-test values decline, and you would slowly see crop yields decline because the availability would slowly decline over time.
Don't forget, if you enjoyed the podcast, then recommend it to a friend or colleague. And as always, rate, review, and follow on Apple Podcast or Spotify so you never miss an episode. And for more information, go to teagasc.ie. I'm Michael Hennessy. Thanks for listening, and I'll be back next week with more tillage news and advice.